Okay. Law of mass action. A quantitative relation that connects the concentration of reactants and products with the extent of chemical change is known as law of mass action. A quantitative relation that connects the concentration of reactants and products with the extent of chemical change is known as law of mass action. It states that the rate of chemical reaction is proportional to the active mass, that is the concentration of the reacting substances. Specifically, the rate of an overall chemical reaction is proportional to the product of the active masses of all reactants is raised to the power equal to its stoichiometric coefficient in the balance equation. Active mass is a molar concentration and X phase by closing the symbol of the substance in a square bracket or symbol C at the base of which the symbol of substance is placed, that is A or C. It is considered a general reversible reaction A plus B, C plus D. Application of law of mass action. To reversible reaction. According to law of mass action, the rate of forward reaction and rate of backward reaction, where Q1 and Q2 are the rate of constant of forward and backward reaction at equilibrium, R1 and R2, so that we can write Q1A B equal to K2 CD. So that Q1 over K2 equal to CD over AB. So Kc equal to, we can write Cc dd Ca Cb. Equation first is the required expression of the law of mass action for the reaction of the following type A plus BB plus Cc dd. The equilibrium constant in terms of molar concentration is given by Kc equal to C to power C d to power D over e to power A B to power B. For gaseous reactions, the partial pressure of substance is directly proportional to its molar concentration. Therefore, in a gaseous system, concentration terms can be replaced by the partial pressure terms. Thus, the equilibrium expression becomes Kp equal to Pc to power C, Pd power D, P power A, and Pv power B. Where Kp is the equilibrium constant in terms of partial pressure, Pa, Pv, Pc, and Pd are the partial pressure of the respective species A, B, C, and D. Relation between Kp and Kc, the equilibrium constant Kp and Kc are related to each other, and the relationship can be established by means of the ideal gas equation Eb equal to nRT. So P equal to N by RT, so I can write CRT, C equal to N by B. This is considered a general gaseous reaction as the equilibrium constant in terms of concentration Kc equal to C to the power C, D to the power D over A to the power A, B to the power B. The equilibrium constant in terms of partial pressure Kp equal to Pc to the power P, Pd to the power D, Pa to the power A, Pb to the power B. So we can write Kp equal to C to the power C, RT to the power C, similarly D to the power D, RT to the power D, C to the power A, RT to the power A, Cb to the power B, Cr to the B. So again we can write C to the power C, C D to the power D, C to the power A, Cb to the power B. RT equals C, RT equals D over RTA, RT equals B. So we can write RT plus C plus D. And again, we can write C plus D minus A plus B. So RT delta N, number of moles of product minus number of moles of reactant. Case first, when the number of moles of product equal to number of moles of reactant, so delta N equal to 0. In case of hydrogen and iodine reacts to form hydrogen iodide, Kp equal to Kc. Case second, when delta N equal to positive, that is the number of moles of product greater than number of moles of reactant. Case of dissociation of phosphorus pentachloride, phosphorus trichloride in chlorine gas for source reaction Kp is greater than Kc. Case third, delta N equal to negative, that is number of moles of product less than number of moles of reactant. In case of Hayward's process, manufacture of ammonia from nitrogen and hydrogen, Kp is greater than Kc is greater than Kp. Unit of Kp and Kc depends upon the nature of reaction. If number of moles of product is equal to the number of moles of reactant, equilibrium constant Kp and Kc does not possess any unit. If number of moles of product is not equal to the number of moles of reactant, equilibrium constant Kp and Kc possess certain unit. Application of law of mass action to homogeneous equilibrium. Law of mass action can be applied to gaseous phase equilibrium as well as liquid phase equilibrium. Gaseous phase equilibrium having delta N equal to 0. Number of moles of reactant is equal to number of moles of product, S2 plus I to 2Si. Where Kp equal to Kc, now let's apply the law of mass action. For flowing equilibrium, S2 plus I to 2Si, let A mole of hydrogen and B mole of iodine are heated in a vessel, volume B. After certain time, Tx mole of hydrogen combines with X mole of iodine to give 2x mole of hydrogen iodide. So, this reaction initially concentration of A Okay. Hydrogen reacts with iodine to form hydrogen iodide. Initially, A and B moles of the reactants, hydrogen and iodine, and at equilibrium, the product of hydrogen iodide is 2x, so A minus x and B minus x mole of the concentration of hydrogen and iodine. Calculation of equilibrium constant Kc, applying the law of mass action to the above equilibrium, Kc equal to Si square, Si over hydrogen and iodine. We know that molar concentration, number of mole over volume in liter. At equilibrium, the concentration of hydrogen A minus equal V, molar concentration of iodine B minus X of V. So molar concentration of hydrogen iodide 2x over V. So equation first becomes, so that Kc equal to 4x square A minus A B minus equation 2. From equation 2, it is concluded that Kc is the independent of volume because of B. It does not appear in the expression 2. For all gases phase equilibrium having the equal number of mole of reactant product, the change in the pressure or volume has no effect on the equilibrium constant. Calculation of every constant Kp applying the law of mass action to the above equilibrium, Kp equal to Psi equals square over Ps2 Pi2. Total number of moles of chemical species in equilibrium. Let P is the total pressure of the gaseous mixture, partial pressure number of mole over the total number of mole. Total pressure at equilibrium, Ps2 A minus X over A plus B to P. Similarly, total pressure Pi2 B minus X A plus B multiply P. Partial pressure of SI, Pi 2x over A plus B 2. So Kp equal to, we can write, and equation 4. Equation 4 is the independent of pressure of volume term. Equation 4 also gives similar conclusion to equation 2. Characteristic of gas is equilibrium having delta n equal to 0, relation between Kp and Kc. Since there is no change in the number of mole of reactant in product, the value of Kp and Kc are equal. Effect of change in temperature for the reaction S2NI2 gives hydrogen iodide. Kc equal to Kf over Kb, where Kf is the forward rate of reaction and Kb is backward rate of reaction. In the above equilibrium, forward reaction is exothermic and backward is endothermic. When the temperature increases, it favors endothermic side reaction. In the above case, backward reaction is favored by increase in temperature, so the value of Kb increases more than Kf. Low temperature favors the forward rate of reaction. Effect of change in pressure. In the expression 2, Kp is independent of pressure, so change in pressure will have no effect on equilibrium. Effect of change in concentration for the equilibrium, hydrogen and iodine is hydrogen iodide, Kc equal to Si square over S2I2. At particular temperature, the equilibrium constant value is fixed. Let concentration of S2 is increased at a particular temperature in the above reaction. To keep the value of Kc constant, either the concentration of Si should be increased or the concentration of I2 should be decreased, or both take place. Addition of one of the compound in the equilibrium condition shifts in the equilibrium to consume the added reactant. Effect of inert gas, there is no pressure term in expression Kp and Kc. Hence, addition of inert gas either at constant or the constant volume has no effect on equilibrium state. Gases face equilibrium having delta n greater than 1, number of moles products not more reacting. In this example, molar concentration of each chemical species at equilibrium is given below. So Cl3 and Cl2. Now applying the law of mass action, we can write Kc equal to x squared over A minus xb equation second. The expression Kc has the volume term a denominator, so above equilibrium will be affected by the change in the volume of reaction. So Kp, applying the law of mass action, Kp equal to PCl2, PCl2, PCl5 equation third. For the above equilibrium, total number of moles of equilibrium, A plus X. So the partial pressure of each concentration term at equilibrium is calculated by partial pressure number of moles of compound over total number of moles. We'll write total pressure. So we can write PCl5, PCl3, and PCl2. Now the equation second becomes, and the expression Kp has pressure term of numerator. So above equilibrium will be affected by change in pressure. The effect of pressure can be derived as follows: when the values of X is very small, it can be neglected. Equation 4. Hence, degree of dissociation of phosphorus, PCl5 is inversely proportional to the square root of pressure. Hence, increase in the pressure, decrease of PCl5. Characteristics of gaseous phase equilibrium, delta n greater than 1, relation between Kp and Kc. We know that Kp and Kc from above relation, Kp is not equal to Kc. Effect of temperature, increase in temperature increase the volume. From the equation Kc, it is calculated that to keep the value of Kc constant, the value of X increases with increase in volume. So the dissociation phosphorus pentachloride increases with increase in temperature. Effect of pressure. The effect of pressure on the equilibrium can be explained on the basis of when the value of X are neglected in addition and subtraction in denominator, so that phosphorus proportional to pressure proportional to 1 over X squared. Hence, increase in pressure, the value of X, and it decreases the dissociation of phosphorus pentachloride and equilibrium shifts towards left. Pressure is proportional to, well, inversely proportional to value of X. Effect of PCl3 and PCl2. When the concentration of PCl3 is increased, the concentration of PCl2 decreases and concentration of PCl5 should increase to keep the value of Kc constant. As evident relation Kc equal to effect of adding inert gas. In the above equilibrium, inert gas can be added either at constant volume or at constant pressure. Addition of inert gas at constant volume. When inert gas added at a constant volume, then total pressure of gas mixture is increased, but the partial pressure of each component does not change. Means total pressure of gas increases by equal to the partial pressure of inert gas. So degree of dissociation will not increase or decrease. When inert gas is added at constant pressure, the partial pressure of gas decreases and it increases the values of X as evident from the relation. So dissociation of phosphorus pentachloride is increased, our equilibrium shifts towards right. Gaseous phase equilibrium having delta n less than 1, but delta n does not equal to 0. Number of mole of product less than number of mole of reactants. In case of reverse process, let us start experiment with the a mole of nitrogen and B mole of hydrogen under appropriate condition. Nitrogen and hydrogen combine to give ammonia. Since 1 mole of nitrogen combines with 3 mole of hydrogen to give 2 mole of ammonia at equilibrium condition. The amount of nitrogen and hydrogen remaining at equilibrium are A minus X moles, B minus T moles respectively. Let volume of the vessel in which reaction is carried out at V liter. Calculation of Kc. Applying the law of mass action to the above equilibrium, the value of Kc of is given by Kc equal to at equilibrium, molar concentration N2, hydrogen and concentration of ammonia. I can write Kc equal to equation 2. The expression Kc has the volume term at numerator, so above equilibrium is affected by change in volume. If the value of X is denominator is assumed to be negligible, then volume is found to be inversely proportional to X. So decrease of volume should be increase the value of X, and it increases the rate of production of ammonia. Calculation of Kp. Applying the law of mass action to the above equilibrium, the value of Kp is given by question 3. Let P be the total pressure of equilibrium system, the total number of moles of equilibrium. So now partial pressure, number of moles of component over total number of moles, multiply total pressure. So Pn2, Ps2, Pns3. We know that Kp equal to so equation 4 is obtained. Characteristics of gases phase equilibrium delta N greater less than 1, but delta N not equal to 0. Relation between Kp and Kc. Kp and Kc are not equal. So Kc equal to effect of temperature. On increasing the temperature at constant pressure, volume of gas increases. From equation 2, it can be calculated that the value of X should decrease with increase in volume to keep the value of Kc constant. Value of X decreases means formation of ammonia decreases, and decrease in temperature favors the formation of ammonia. Increase in pressure increases the rate of value of X to keep the value of Kp constant according to question 4. Hence, increase in pressure increases the value of X, and it increases the formation of ammonia. With increase in the pressure, formation of ammonia increase. Effect of adding nitrogen and hydrogen in equilibrium mixture. According to volume of nitrogen is added into equilibrium mixture, the partial pressure of nitrogen is increased to keep the value of Kp constant according to the equation 3. And partial pressure of hydrogen should be decreased, and partial pressure of ammonia should increases. This happens when the equilibrium shifts towards the forward direction. Similar effect can be studied on the adding hydrogen and ammonia at equilibrium state. Effect of adding inert gas at constant volume. There is no effect on addition of inert gas, but constant pressure, the addition of inert gas decreases the partial pressure of each component according to relation Kp equal to the decrease in pressure decreases the value of X to keep the value of Kp constant. Decrease in the value of X decreases the rate of formation of ammonia. Homogeneous equilibrium in liquid system. An example of liquid phase homogeneous equilibrium reaction is the stratification reaction. In this equilibrium, also law of mass action can be applied. Let us start the experiment by taking a mole of acetic acid and B mole of ethyl alcohol. At equilibrium, let X mole of acetic acid combines with X mole of ethyl alcohol to keep the X mole of ethyl acetate and X mole of water. The concentration of acetic acid and ethyl alcohol at equilibrium are A minus 6 mole and B minus 6 mole in the given volume of solution. Applying the law of mass action to the above equilibrium, we get, let volume of solution be liter, the molar concentration of each chemical species equilibrium. So this relation, now equation first becomes Kc equal to, so equation 2 is obtained. The equilibrium constant is independent of volume of system. Ethanol and ethanoic acid are mixed together in a 1:1 molar ratio at 25 degrees Celsius. 60% of each reactant converted into star. Calculate the value of equilibrium constant for transformation. Let V be the volume of reaction mixture, so number of mole initially, and number of mole at equilibrium. So at equilibrium, for the equation, 60% is reactant is converted into star. So let 100% to equal to 1. So 60% is 0.6 mole. So we can write this 0.6 mole. Now equilibrium constant Kc equal to, so 2.25. 307.2 gram of hydrogen iodide is allowed to undergo the thermal dissociation of 721 Kelvin. The degree of dissociation is 22%. Calculate the number of moles of hydrogen iodide, hydrogen and at equilibrium constant. Also calculate the equilibrium constant for dissociation reaction. Molecular weight of hydrogen iodide 128, number of moles of hydrogen iodide 2.4. So reaction initially and at equilibrium. In the above reaction, for each of mole of dissociation hydrogen iodide, half mole of iodine are formed in the given equation, n equal to 2.4. So alpha equal to 22%, 0.22. Number of mole of iodide at equilibrium, n 1 minus alpha. So 2.4, 1 minus 0.22, 1.872 mole. Number of mole of hydrogen at equilibrium, molar concentration of hydrogen, molar concentration of iodine, molar concentration of hydrogen iodide. Now at equilibrium, Kc equal to S2 I2 over 2Si, so 0.098. Okay. It's all about law of mass action and its application. Thanks for watching, and request you all like, comment, share, and subscribe. Thank you for patience. That's now bye bye. See you again.